talking about decision trees, then this is where we stop. So last time we talked about how entropy can help us divide or like partition the data set into sub data sets so that each sub data set is more pure in some sense, right? More less chaotic, more uniform. So that each sub data set has higher probability of, if you sample a random point from it, it has a higher probability of sampling the same kind of label, right? So today we'll talk about another method that achieves something similar, but through another angle. And this is through something called the chi-square test. So chi-square test in general, it's not specifically designed for decision trees. It is used in decision trees as an application, but I will use this as an excuse to one, sort of refresh your memory about hypothesis testing, and two, to tell you a little bit about how when you do a procedure like this, what kind of implicit assumptions you make that may not be very apparent from when you're actually applying the algorithm. If you've taken a stats course, you might have seen this before, at least the chi-square test. Has anyone seen this before? Okay, does anyone want to explain what it is? You don't have to be correct, I'm wrong all the time. Just this morning my grad student told me my conjecture is like completely wrong. Anyways, yes.
It's a test for independence by essentially checking if proportions stay consistent across different categories.
Okay, yes, so it's a test for checking independence, right? So we're not doing the stratified one. I think that's the one that you're talking about where there are partitions. So this is not the stratified one, the simpler one. Yeah.
Is it a way to check how each feature is like increasing or decreasing the like p-values? Like accuracy, how each feature is increasing or decreasing, like the probability of like success?
Yeah, it's trying to check whether, so that's what independence means, right? So given a feature and a y variable, are the two related? So if it is correlated or anti-correlated, which means it is increasing or decreasing the probability of success, then it will not be independent. So we'll not be able to tell you through this test whether it is correlated or anti-correlated. We are just focusing on pure independence, right? Independence or not. So for that, we'll use the framework of hypothesis testing. So hypothesis testing will first assume, you talked about hypothesis testing in this course, right? Yes? No? Yes? Okay, so maybe someone can explain it to me. So maybe you have seen it in some stats course also, but since it should be like relatively fresh in your mind, right? So yes.
You're trying to compare the null hypothesis versus an alternative.
Right. Exactly. So we assume that the null hypothesis, we make a null hypothesis, then we assume it is true, then we run an experiment, and then we say the results of these experiments, if the null hypothesis is true, how possibly random they are, or if it is not true, what is the probability, the p-value, that this was generated by random chance and was actually not generated by the null hypothesis, right? And if that is the case, we set an arbitrary value. In many cases, it's 5%. Depending on how strong you want your statistical power to be. Some experiments set it at 1%. That's pretty arbitrary. And then what that means is with this percent chance, the data was actually generated randomly by chance. Any distribution, even if the null hypothesis is not true, because we are dealing in world of probabilities, it's not deterministic, right? So that means that even though the data that we are seeing, it may not have been generated by null hypothesis, it could have been generated by chance randomly, right? So when we are talking about distributions, standard, like for example, a Gaussian distribution looks like this. Doesn't actually go there, it just like keeps going there, right? So here, there's a higher chance that if you sample from this distribution, the data will come from somewhere around here, right? Near the mean or the mode. Yes? But with some non-zero probability, it could come from the tail also, right? So if the weight or the total mass of the data being generated by chance is small enough, it lies at the tail, then we say that it is unlikely that the null hypothesis is true. We reject it. Make sense? Okay, so now we're going to apply that to our independence test. We're going to assume that y and a variable that we want to possibly split the data on are independent. That's our null hypothesis, right? And based on that, we're going to do an experiment. So this is called the chi-square test. So what it will do is that it will make an assumption saying that yes, maybe the null hypothesis is true, right? And then it will try to generate some values, EIs, and based on that, it will compare it to actual values that you see in the data, and then it will look at the discrepancy between the two. And that will give a measure of if the two actually align, that means that the null hypothesis is actually true, right? The higher the discrepancy, that means the data is less likely to be generated by chance, which means the null hypothesis may not be true, which means we will reject the null hypothesis, which means that the y variable and the attribute A are actually not independent. And larger this discrepancy, the more the level of dependence. Yes? So this is how the chi-square formula is defined. So we'll first construct a contingency table which looks something like this. So the idea of contingency table is you have the class, which is the y variable, and then the attribute under consideration. So you'll generate one such contingency table for every possible candidate potential atom or the feature that you want to use, you want to test on, right? And then, so there are total number of n data points, and then you will try to see how many times attribute value A, let's say this is A, is equal to 0, co-occurs with class label plus in the whole data. And if that happens A times, you will fill in A. So A is a number, right? A plus B plus C plus D is equal to n. So there are n total data points. And then how many times attribute value and a class label co-occur in the data, you fill in that value over there. That's how you build contingency tables. Contingency tables are not specific to this method. In general, you'll find them in other methods also. Yes? So now let's try to run our test. So the test goes, we are looking at OI, which is the actual value, right? And EI, which is the expected value under the null hypothesis. And then we're going to check the discrepancy between the two. So OI is the actual value. I will go from 1 to k, where k is the total number of values of that attribute, right? Okay, so for O, we'll say if the label is 0, and so the attribute value is 0, and the label is plus, how many times does this actually occur in the data? From the contingency table, we know that that happens A times, right? Now we're going to say, let's look at the expected value under the null hypothesis. So for that, for expected value, what do we do? So if I give you a coin and I say the probability of head is P, and you toss the coin capital N times, what is the expected number of heads? Probability of each head is P, you toss the coin N number of times, what is the expected value of total number of heads? Yes?
P times N.
P times N, right? The expected value of a head showing up in one coin toss is P, in n independent coin tosses is Pn. Right? So that's what we're doing here. This is the probability that it occurs together, this value of attribute and this value of the label. C is for class, A is for attribute. So you multiply that by n. Right? That's the expected value. But we are doing this under the null hypothesis. What is the null hypothesis? That the feature and the y are independent. So if they are independent, that means this probability will divvy up like this, right? That's the definition of independence. So then you divide it up like this. The individual probabilities get split up. The joint probability is equal to the marginal probability, the multiplication of marginal probabilities, right? That's the definition of independence. And now these values you calculate again from the contingency tables. These are marginals, right? So remember in the very first lecture, I showed you a bunch of like joint distribution tables, and I showed you how to calculate marginals from that. You basically sum up across the column or the row. People remember that? No? Yes? Why do I see blank stares? Is it me? Okay, so you see how, can someone tell me how, I mean it's written there, but like if you want to see probability A is equal to 0, how often, with what probability that occurs in the data, what will you do? You will look at probability A is equal to 0, the marginal of that. How many times does that occur in the data? A plus B times. So what is the probability? A plus B divided by n. Yes? So that's what you do here. Same thing for this. Yes, and this follows. So what you have calculated is, under the null hypothesis, what is the expected value of that set? E0 plus of that set. So A is the actual value. Under the null hypothesis, what is the expected value? Yes?
What's the difference between this and a confusion matrix?
That word has different meanings depending on what method they're using on. Can you explain?
Like, isn't a confusion matrix the true positives and the true negatives that comparing those?
Oh, I see. So true positives and true negatives will be like this was actually positive and it was predicted to be negative. There's no prediction here. Right? There's no y hat. There's actual y and the value of the variable. Right? So A is equal to 0. So A can be, let's take, like we had the example of the weather, for example, right? Or like windy or not, right? So A is equal to 0, it's not windy. A is equal to 1, it is windy. So confusion matrix in that context will be like, I'm predicting as play or not play. And then if it was actually play, right? But I predicted it as not play, right? That is a false negative. And then you fill up the whole table like that. There's no y hat here. There's just the attribute value and the y value. It doesn't actually even have to be the y value. It can be, you can do this across different attributes. So this can be attribute 1, that can be attribute 2. That's a contingency table. If you want to compare if two attributes are independent or not, you can just do that. There doesn't even have to be a y. Does that answer the question?
Yeah.
Okay, good. So now we compare the actual value and so this is the observed value, like what the data actually tells you. And you have the expected value that you just calculated under the null hypothesis. And then you plug it into the formula, not to do the calculations, that's the final value that you get. Now what you do is that this thing is, that's the chi-square statistic that you get. Higher this is, what can I say about my null hypothesis? Higher the chi-square statistic, what can I say about the null hypothesis? Yes?
The higher it is, the more unlikely it is.
Right. That means that the discrepancy between the expected value and the actual value is bigger. Right? That means my null hypothesis of independence is likely to be wrong. wrong, which means I should reject. Right? Now, how does this translate to p-value? People who have done hypothesis testing in this course or before, how do I do that? So this will give me a number. This is this number. How do I get a p-value from this? Yes.
You integrate the distribution from 0.57 to positive infinity, and that's the chance that you get a value. If the null hypothesis is true, that's the chance that you get a chi-squared statistic that looks bad or worse.
I like your intuition, but this is the y value. This is not the x value. You want to But you're right, yeah. I'm just, it's part of the job for me to be pedantic and split hairs, right? So I'm not trying to embarrass anyone if you're wrong. It's okay to be wrong. I just have to, if I correct you, that's okay. That doesn't mean that you should not speak up, right? Okay, great. So your intuition is right. So what we want to do is, like I said here, so this is the value that we get, that's the y value. How unlikely it is under the standard distribution that I'm assuming. So here, the way that the experiment is conducted, what we do is we can say that in an asymptotic sense, using some multinomial theory, asymptotic theory that we will not go into, is that this thing can be well approximated by a chi-square distribution of a certain degrees of freedom. So what we do here is we get this value, we look at the chi-square distribution table that you get, and then from that you can check what this tail mass is. So for example, if this is the chi-square distribution, this is 0.57 that you get, the tail mass is this, this might be, this will give you the p-value. Does that make sense? So you calculate this chi-square table, statistic, then you look at the table, or if you have access to this is the y, you get access to the x, and then you integrate. Just looking at the table is easier. That's what practically statisticians will do. And if you've taken a statistics course, this is what they will teach you. That's the algorithm, right? Create the contingency table, look at what the OIs are, the actual values, calculate the EIs, which are the expected value, get the chi-square statistic, look at the table, get the p-value. Yes?
Can you just clarify why higher values mean more unlikely to have an effect?
So when I say effect, I mean it is more unlikely that our null hypothesis is true. So see, intuitively, OI is the actual value, EI is the expected value. The larger this difference is, the expected value and the actual value are mismatching.
You can reject the null hypothesis.
Which is that they are independent. If they are mismatching the expected value under independence and the actual value, there is a larger discrepancy. That means the assumption of independence is actually not likely to be true. How not likely it's going to be true is this tail mass. So you can set a tail mass that you are okay with, which is defined by the p-value. That if this statistic could have been generated by chance and the null hypothesis is actually true, the chance of that happening is less than, let's say, p is equal to 5.05%, then I don't reject it. If it is greater than, I reject it. Yes? Questions? I know you have seen this before, but hopefully this gives you a slightly new perspective of how, things work under the hood. Okay, great. No questions? Sure? Okay, first time I saw this, I had many questions. So you guys are probably smarter than I am, which is great. Otherwise, please go back. If there are doubts, just come to the office hours or something. Right? Okay, so now let's move on and let's talk about some regularization stuff. So we are building the tree, and we talked about when we have the pseudocode of the recursion. We talked about what are some stopping criteria that we can use. So if we are building the tree till we are we have exhausted all options, then we can maybe see that there are no examples left. That's a stopping criterion. Or a node that we have arrived onto is already quote unquote pure. So like further splitting will not improve the chaos or the entropy or the independence, because they're already highly, like with the correlation 1 that's happening in that node, right? Or there are no attributes left for the split. But it's also possible that what's going on? Why does this not show up? Okay. So, but it's also possible that sometimes when we are building up these trees, the trees may possibly overfit, right? So how do we stop that from happening? So there are methods that can help you. Maybe you can do some post-pruning after you have built the tree. You set aside a validation set, right? And you test your tree, you build it on the training set, you test it on your validation set, and then you apply some pruning steps and see if the accuracy on the set aside validation set improves. And if it does improve, then you prune. If it does not improve or it worsens, then you don't prune. So this gives you sort of like a sanity check that you have built the tree on a set of data, and then you apply the tree on a different set of data points and see how it performs, right? So these methods are called post-pruning because you've already built the tree. There's some methods are like pre-pruning, which is like as you are building the tree, you set some hyperparameters, and you say that I'm not gonna grow my tree beyond some depth k, for example, which is a hyperparameter, right? Or you can say that I want to have a minimal, let's say some p number of examples in each leaf node, right? Yes. Or you can say I will not split if the purity is above a certain threshold level tau, right? So all of those things can be done, or you can do the chi-square test and see, or there are other statistical power tests that can tell you whether splitting a node is actually statistically relevant or not, right? Yeah, so the penalty terms is all of those other hyperparameters that I mentioned. Yeah, so I just mentioned all of these. So here is a particular example that we can see of whether we should prune or not. So the idea is that you have built the whole tree, and then, so let's say this is your tree, and pruning means that basically you sort of like collapse the entire subtree into a single node, right? And again, you build it on the training data, and you test it on some validation data which has zero overlap with the training data, and then based on that, you check whether replacing that entire subtree with a single node, is that actually useful or not? Does that actually generalize on unseen data or not? Right? We define some measure of gain, which could be just, for example, validation accuracy, that can help us understand whether we should actually prune or not. It's like designing a scoring function, and then we keep repeating it till there is no other, that further pruning will not give you any gain in terms of your scoring function. So here is a particular example. Let's say using your training data, you have built this tree, and then you have some test data, which is that is my pruning set, right? So the tree was built like this, and then I'm testing it using data that looks like that, right? So those are the errors that you get on the test data. So now let's say I defined gain as the number of inaccuracies that this tree is making, right? So this is my tree when applied to the validation set. So here the red numbers are mistakes or inaccuracies. So right now this tree on the left hand side, if I decide to prune on the left subtree of x2, it's making 3 mistakes, right? if I actually prune this and replace this with a single node, that will be my leaf node, what will be the majority symbol there? What will be the majority label? What will be my prediction? It will be plus, right? It's built using the training tree. So it will be, this will all be labeled as plus. And in that case, how many inaccuracies will be there? 2, right? Because there are 2 negatives and 3 positives, they'll all be labeled as pluses. Yes? So in that case, there will be 2 accuracies, 2 misaccuracies, 2 mistakes. Now there are 3 mistakes. So if I prune it based on the validation set, I get a gain of 1. So by this algorithm in this data set, it actually makes sense to prune the left subtree. Now obviously this is a toy example where we are not going to count just the number of accuracies and we just prune if we get a gain of 1. In practice, it has to be something more substantial, right? But hopefully this gets the intuition across. Yes?
So over here, the labels mean which one has majority, right? So
Yeah.
like on the right, like subtree of the left tree, why is it minus when there are 2 pluses and 1 negative 1?
Okay, so good, yes. Great, thank you for asking this. So this is the validation set. This is the test set. It was not built using this. It was built using this. So whatever test data set comes, I'm not going to decide the majority based on what's in the test data. It's going to make predictions based on decisions that have already been made. This thing is always going to be that. This thing is always going to be labeled negative, based on, because in the training data it was like that. Right? Good question. Yes, please ask questions. Make sense? And similarly, if we try to prune on the right hand side, you will see that it's actually worse. So pruning on the right subtree on x2 is a bad idea because the gain is negative. Yes? Similarly, if you try to prune right at x1, the same algorithm applies and the gain is still negative. So it makes sense to prune at x2. So this is my new tree. Right? And we run the same algorithm again, we'll see that there is no further gain possible, we stop pruning. Yes?
If the pruning set comes from the test data, then isn't there like leakage over?
Okay, very good. Yes. So that's why I said validation set. So there's a training data set, there's a validation data set, and there's a test data set. So I use the term test data set here just to specify that it's not part of the training data. But practically, you have a training data set, you have a pruning data set, which is the validation set, and you have a test data set, and there's no overlap amongst all of these 3. Yes, good question. Yes. You don't want that kind of leakage to happen, right? Great. So again, if we run the same algorithm again, you'll see that there's no gain possible, and so we are done pruning by the standards that we have set for the pruning algorithm. Great. So with that, let's try to get some intuition about what decision trees are doing, like in a sort of like a geometric sense. So you have done linear classifiers, right? We have talked about that in this class. Yes? Right? So what do linear classifiers do? They learn a linear boundary and they divide, let's say it's a 2-class classification problem, they'll divide the feature space into 2 half spaces. One half space is one label, the other half space is the other label, right? Yes? Decision trees are also partitioning the feature space, but instead of learning a single linear boundary that can be an arbitrary hyperplane, they are splitting the feature space by dividing it up using axis parallel boundaries. So this is feature 1, this is feature 2. When I say that split on x less than 0.43, I'm saying this is 0.43, everything here is a different data set now, everything here is a different data set. Right? And then within that subset, I create other axis parallel boundaries. It has to be axis parallel because I'm splitting on a feature value. Right? So it will create other additional axis parallel boundaries, and I'm going to keep doing this till each cell is pure. Right? And each cell here signifies the leaf node of the tree. So basically, I'm dividing up the feature space into rectangles or hyperrectangles higher than 2 dimensions, where each cell is as uniform as possible, as less chaotic as possible. Right? Hopefully this also gives you the intuition about how powerful decision trees are. So there's a theoretical result that says that decision trees can model any function given enough depth. And you can see here intuitively why that is true. Because I can keep dividing up, even though I'm just using axis parallel boundaries, I can keep dividing up my feature space into smaller and smaller cells till I get individualized smaller rectangles, hyperrectangles, which are perfectly uniform actually. But I don't want to go all the way down. I don't want hyperrectangles which are too small, because that may not generalize well. So that's where pruning comes in, where maybe I combine certain smaller hyperrectangles into bigger hyperrectangles, which are not as pure, but still they generalize better on unseen data. Yes? Questions? Okay, great. So with that, our discussion of decision trees is over. So we'll delve into support vector machines. We'll just start because we have 10 minutes, and that's how the lecture is designed. If you have to check the lecture schedule, SVMs, we'll keep talking about it in the next lecture also. So what are SVMs? So these are extensions of linear classifiers. You still have, let's say we are working with two classification problems. We want to learn a linear boundary, but let's make a further assumption that the data is separable. So what does that mean? That means we are looking for a linear boundary which perfectly separates the data, and there exists at least one linear boundary that can perfectly separate the data. Right? So this is the parametric form of a perceptron. We talked about perceptron. Yes? Okay. So we are going to expand this into something a little more complicated, and so this stuff we have already done, right? Decision boundaries for linear classifiers are hyperplanes in d-dimensional spaces. So we're going to generalize them to something a little more substantial. And this is the intuition. So like I said, assume that the data. What's going on? Does anyone know why does this happen? Because the different slide, it's supposed to sync, right? I've never seen that before. Okay, so this is my data. There are two labels, and the data is perfectly separable, which means there exists one linear boundary that can perfectly separate the data. Right? So this is my hyperplane. Everything above is the hyperplane is +1, everything below it is -1, right? Now here's a claim. If there exists at least one decision boundary, there exists infinitely many. If the data is perfectly separable. Is that correct? Yes.
I mean, you could probably move the line like infinitesimally like small and then keep doing that.
So you can move it like really small,
Yeah.
and then it will still be, because there's infinite number of real numbers, right? Yes.
There's like, you can take any line that goes through that space cleanly and it'll be valid, because we
Yeah.
don't know the rest of the size.
Right. So there can be many possible decision boundaries here, right? So which one is the best one to use? Intuitively. Let's not go into the maths, right? Yes.
The one that creates the most separation.
the most separation? Can you define the most separation?
In terms of between.
All of them are giving me equal separation, right? The data is being perfectly separated. So it's with probability 1 that there's zero training error. So I feel like you have something else in mind. Yes.
Like the distance between the points and the boundary itself.
Is
Like you want that to be maximized.
right. Yes. You have the same idea, right? Do you want to add something or same thing, right? Yeah. So we want to find a boundary which is maybe closer to the middle, right? Why is that? Yes.
Because if there's like a new point, it won't be confused. about
Right.
it.
So is there an implicit assumption that we are making here? How do you know the new point will come here and not over here? How do you know? So there's positives, there's negatives here and positives here, and we are saying this is the best possible boundary. What if the negatives look like this? But the sampling process has given me this. It's certainly possible, right? But yes, you have, yeah.
I guess like there will be like a higher probability of it being
Right, so in
closer.
general, in the number of worlds that exist, right, so remember like I said, all models are wrong, but most likely scenario is that higher separation, every new data point that comes in will give me better generalization accuracy if the boundary is as far away as possible from each class. Right, so when we did the statistical test, the chi-square test, what is the implicit assumption that we made here? There? Yes.
Independent, like we assume they're independent to start.
We checked for independence. That's the null hypothesis which we rejected. The implicit assumption there is that the smaller number of samples that we are getting can be modeled by this asymptotic procedure, which is the chi-square distribution samples. So that sampling, it may not actually represent that distribution, right? But we are making that assumption. So that is the implicit assumption. Every time you do a statistical significance test and you compare p-values, that's the assumption you're making, always. That's true for all of these statistical power tests. Okay, so there are many possible boundaries. So like I said, new test data points, like you said, new test data points might come in. So we don't want boundaries, we want to reject boundaries which are too close to given data points. So we want to choose boundary which is as far away as possible. And then, so this is called, the D is called the margin. So this is the margin from the negative examples, this is the margin from the positive examples. And I think this is a good place to stop. Yeah. So we'll continue from here.